Hi there, welcome to the shadow paper for May 2017 EdXL 1H. So what have we got here? Well, this is a paper for you to have a go at before with very similar questions, or if you had to go at the real paper, this is an opportunity for you to practice a little bit more. So let's look at our first question. The scatter graph below shows the highest temperature on a day and the number of hours of sunshine the same day. There are 14 British towns represented. Okay, so there's 14 of these, okay? So they represent sort of one town, and the idea is that this one here has about, what should we call that, 9.5 hours of sunshine, and then if you go along, it also has a maximum temperature there of 13. So the first question is, which point is the outlier? Well, there's one point that doesn't follow the pattern, and that's this point over here. Let's try and be accurate if we can. That's 0 to 2, that's 1, so I'm going to say 1.5, and the maximum temperature was 22. Okay, so that's my outlier. Write down the type of correlation shown by this graph. So correlation, we're going to talk about positive, no correlation, or negative. So I would say that this one is fairly positive. Okay, so positive correlation. Another British town, this is a new one, had a maximum temperature of 17.4. 17.4, where would that be? That would be, if there's 17.4 is pretty close to this, this line here. So, estimate the number. Estimate means you're going to use a graph, typically. So, estimate the number of hours of sunshine that it had. Well, if it's 17.4, I can go along, and then I can go down. So this doesn't have to be perfect. There is a leniency built in here, but I should try and get pretty close. That would be 13. That would be 12.5. I'm going to say 12.2. 12.2 hours. One mark for clearly using the graph typically on this one. Tracy says temperatures are higher on days where there is more sunshine. Temperatures are higher on days that there are more sunshine. More sunshine, higher, yep, okay, I would agree with that. So does the scatter graph support what she's saying? Well, we're going to say yes. Give a reason. Yes, because, and I would say something like, as the number of hours of sunshine increases, as the number of hours of sunshine increases, there is, maybe we can say there is typically more, what are we talking about? Hours of sunshine, typically, let's say a higher temperature. Okay, it doesn't have to be, you know, an essay, but something along the lines of that. Okay, there we go. That's our first question then. Second question, express 72 as the product of these prime factors. Product means you're going to write something with multiplication signs. So for example, if you wanted to write 15 as a product, you could say, well, it's the same as 3 times 5. Prime factors mean the things that you write it in have to be prime numbers. And actually, you see here that they are both prime numbers. So we're going to do that, but with the number 72. So you might have seen something like this before. You break it up into a tree. You can go anyway, you'll get the same answer. So I'm going to do 72, and I'm going to go in with, let's do 8 and 9. And the way I like to do this is you only sort of take your pen off the paper if it's not a prime number. So what do I mean? I'll show you. So 8 and 9 are not prime numbers, so we're going to keep going. 8 is the same as 4. 4 is not prime. And 2. So I don't take my finger off the paper. What I'm going to do for this one, just to show you in real time what I would do if I were you, is I end up circling it. So I don't forget it, because that's what a lot of people do. 9 is 3, okay, and another 3. Okay, that one's done. So you don't have to literally do this, but it's just to sort of give you an idea. Now, what you can notice clearly is that 4 is not finished. So that's why I like doing this technique. So there we go. That's how we know we're done. So the final thing we do is we take all of this and we write it as a product. That's with that multiplying sign. So 2, 2, 2. So 2 times 2 times 2. There's 3 of them. a 3 and a 3. And for this question, that would actually be enough. Sometimes, though, you might have to write it in this format. You may have seen this before. Okay, this is called index form. So either is fine for now, but I might just leave it there to be on the safe side. Okay, number 3, we're multiplying some decimals. So I'm going to use a particular technique, and you're going to see why on the next question, if you have a look at question 4. So if you do the column multiplication method and you get the right answer, that's fine. You could just skip this one, okay? But I'm going to show you a way that you can reliably get the right answer each time, and it kind of links to what the other one is. So what you do is you partition the numbers. So partitioning the numbers means you call that 50, and you call it 3, and you call it 0.2. Now, why do you do that? Well, if you break it into its bits, it makes the multiplications much easier. We do the same with the 4.6. I call that 4, and I call that 0.6. And then you put those in. So what's the idea? Well, this is really the same as your column multiplication, but what you're going to do is you're going to multiply some separate times and put it all together. The bits here will be really, really easy, so they're easy for you to work out. So what do I mean? Well, 5 times 4 is 20, isn't it? Make it 10 times bigger, it's 200. So that's really quick. 3 times 4, really, really quick. 5 times 6 would be 30. Make it 10 times smaller, 3. Make it 10 times bigger. So this will actually end up still being 30. 3 and 6 is 18. Make it smaller, 1.8. 2 and 4 is 8. Make it smaller, 0.8. 2 and 6 is 12. Make it smaller, 1.2. Make it smaller again, 0.12. Finally, you just collect all the bits together so you can sort of write them in a nice way that they slot together easily. You can do a bit of this in your head if you want, but we're going to add that one, that one, that one, the 1.8, the 0.8, and the 0.12. And you would just add all that up. But in practice, you'll probably do something like this. You'll probably say, well, that's 242. What's this together? Well, that's going to be 2.6. And then I could maybe just add that on there. So actually, I'll just call that 2.72. All right. So if we put that all together, you get what? You get 244.72. So I'm deliberately going a bit slower because look, there's actually 3 marks there. So there's no point messing it up. You need to check that you've got a method that reliably works for you. Now you're going to see why we just did this. Have a look at question 4. What does this look a bit like? Looks a bit like a grid. So this is a square. The area of square ABCD is 28 centimeters squared. Okay. Show that, right. Lots of people find this kind of question really, really difficult, but you just need to start trying to work some stuff out and then try and understand why all the information is there. If you have area, that's when you multiply typically sides and you work things out, right? So if we wanted to find this one, that's 5 times 5, that's 25. This one, 5 times x, 5x. This one, 5 times x, another 5x. This one, x times x, x squared. So according to the algebra that is in front of me, that is drawn here, according to the algebra is saying that my answer is x squared plus 10x plus 25. Underneath, however, somebody's saying the area is 28. So this is kind of I suppose this is the question. This is the question telling me it's 28. Well, which is it? Is it this or this? It's both. So that means I must be able to say that this is equal to this. In other words, x squared plus 10x plus 25 equals 28. Now, I've taken this into account. Is there anything going on here that will give me a clue for what to do? X squared, that looks like what I've got. 10x, that looks like what I've got. This is a little bit different. How could you get that 3? Well, I take away 25 from both sides. So probably because it show that, I would just sort of do something like this to make it really, really clear. So x squared plus 10x equals 3. Number 5. A frame is made in the shape of a rectangle using 5 pieces. 1, 2, 3, 4, 5. So it must be including that middle bit. Each piece weighs 2.5 kilograms. Okay, so work out the total weight of the frame. Note, re-record number 5. Okay, a frame is made in the shape of a rectangle using 5 pieces. 1, 2, 3, 4, 5, presumably. Each meter weighs 2.5 kilograms. Work out the total weight of the frame. Okay, so the fact that it's a rectangle means I can put some numbers on here straight away. However, there's the piece in the middle as well, and there's this suspicious right angle over here. So if this is a 4 and this is a 3 and this is a right angle, I can use Pythagoras' theorem for this one. This is the one where we're adding because we're finding the long side. So 3 squared plus 4 squared, and then the square root of that. So I'm looking for the root of 9 plus 16, or in other words, the root of 25, which is 5. Okay. So now that I know that that's 5, well, 1 kilogram is 2.5. 1 meter is 2.5 kilograms. So how many meters are there? Well, there's 2 3s, there's 2 4s, and there's a 5, so 6 plus 8 plus 5. What's that going to be? That's 14 plus 5, so I've got 19 meters. Okay, so 1 meter is 2.5 kilograms. So I've got 19 meters. So I've got to multiply that up 19 times, haven't I? So 19 times 2.5. How am I going to do that? I'm going to use a grid. So I'm going to do 2.5. So 19 times 2 is 38. And then what's a half of 19? Well, a half of 18 would be 9. And then split the other one is 0.5 then. If I put that together, that's going to be 47.5 kilograms. Okay, so that's how much this frame should weigh. What have we got next? Next up, we've got, here we go, question 6. So the equation of line 1 is this, 4x plus 1. So what does that look like? Intercept of 1, 4, something like that. The equation of line, that's line 1. The equation of line 2 is this thing here. Okay, this is much harder to quickly think about because of the way that it's written. I'll come back to that in a moment. Show whether these lines are parallel to each other. So what does it mean if they are parallel? It means they have the same gradient. So because I've just done a little bit of thinking before I jumped in, I can see what the gradient of line 1 is already. When things are written in this kind of format, we typically say y equals mx plus c. It's very, very useful because the m bit, in other words, the bit that goes with the x in the front, is the gradient. Okay, so the gradient of the top line is 4. So what's the question really asking you? It's saying, well, this is 4 for the top one. Is it 4 for the other one? So how are you going to find out? Well, you're going to take this equation here and you're going to do some work to it to see if when you say y equals, if it also has a 4. I'm not really interested in the other parts because gradient, being parallel, is only about being the same gradient. It doesn't really have any other implications. Okay? So what could I do? It seems to me that a good first step would be to take the other stuff that's not about the y and to manipulate to get rid of that. So if I add 16x to both sides, I would get 4y plus 2 equals 16x. And if I take away 2 from both sides, I would get 4y equals 16x minus 2. So that's getting a bit closer. Now, it's got to be y equals. You can't have 4y equals. That doesn't work. So how do I get y equals? Well, what I need to do here is I'll need to divide both sides by 4. But a little shortcut I'm going to show you is that if you just divide everything, every term by 4, that's the same thing. So 4y divided by 4 is y. 16x divided by 4 is 4x. And minus 2 divided by 4, well, you could sort of just write it like that, because as we said, it doesn't really even matter. It's minus a half or minus 0.5, but we're not really interested in that. What are we interested in? Is the number in front of the x here, the number that goes with it, a 4, a positive 4? Well, yes, it is. So show whether they're parallel. So yes, they're parallel, as gradient is 4 for both. And I've just shown that, I haven't just said that. So that's what we could do. Number 7, there are 15 boys and 30 girls in the club. The club has a competition. The mean score for all the club members. So we've got boys, girls, all. So it seems to sort of be... So for question 7, I've jumped ahead a little bit to sort of save us a bit of time. Let's take a look. There's 15 boys and 30 girls. The club has a competition. The mean score for all of the club members is 80. The mean score for just the girls is 75. Work out a mean score for the boys. So I've divided this up into boys, girls, and then all members. We've got total number, so this is total score. Number in sort of number in the group, and then I've got the mean score. So the reason why I've got these sections is because the mean, remember, is given by the total of something divided by the number of bits of data, or the number of people in the competition here. These numbers, I've just got these from filling those values in from the question. And the question is, what's the mean score for the boys? So to find this out, it's not as easy as just working with these, I'm afraid. It's not going to be 85, okay? What we need instead is we need the mean score for the boys. And that's the total score. That's the total score for the boys divided by the number of boys. So we're missing an important piece of information. So how are we going to find this out? Well, we're going to try and find out by using other parts of the table. The first one I'm going to say is, if I assume that they are all boys or girls, then 15 and 30, what I can do is I can add those numbers. So in the club in total, there's 45. What else can I do now? Well, unfortunately here, I still can't do anything, but I've got 2 bits of information and I can use that to try and find out a third piece of information. In fact, I'll just put that as orange so you can see that that's a new one that we've got. So what was the total? What was the total for all of it, for everybody in the group? Well, the total, which we don't know, divided by the number of people, which is 45, must have been equal to the mean, which is 80. So how could I find that total? Well, I could do the inverse. I could times by 45. So 45 times 80 will tell me the total. How would I do that? Well, I could do 40 and 5 times by 80. 4 times 8 is 32. Add a 0, add a 0. 5 times 8 is 40. Add a 0. So 3,600 is the total score for everybody in the competition. I'm going to do the same process again now with just the girls. So the girls got a mean score of 75, which was made up by the total that we don't know, divided by 30. So I'm going to do 30 times 75. 75 times 30. 3 times 7 is 210. Sorry, 3 times 7 is 21. Add a 0, add a 0. Now it's 2,100. 3 times 5 is 15. Add a 0, 150. Put it back together and I get 2,250. So I am allowed to actually add these numbers to make up this number or take away, because the idea is the score for the boys plus the score for the girls is this total score for everyone. That I am allowed to add. The same as I was allowed to add and subtract these ones. So what's that missing number? Well, if I added on 50, I'd have 2,300. Another 300, 2,600, and 1,000 would take me there. So that must be 1,350. I'm almost there now. 1,350 divided by 15 is how we get the mean. That's what we said. So let's do that. 1,350 divided by 15. What's the easiest way to do this? Well, one way that I would recommend doing it is partitioning. So if I break the number up into, let's say, 750 and 600, how many 15s go into each of these things? How many times does 15 go into 75? 15, 30, 45, 60, 75, 5 times. If you make the number 10 times bigger, it will go in 10 times more. How many times does 15 go into, say, 60? 15, 30, 45, 60, so 4 times, and then 10 times more. So, if I put these numbers back together, the mean score for the boys is 90, and that's the final answer, 90. Bit more work involved there, but you can get very quick at doing that one indeed. Number 8, write 2.09 times 10 to the minus 4 as an ordinary number. Ordinary numbers are things like these and these and these. These are ordinary numbers, okay? So there's a couple of ways you can do this. So many ways, really. I'm going to just do the old-fashioned way, which is that you just write out your original number and you think of this as a set of instructions. So this times by 10 to the something means move the decimal place. If it's a negative, it means move it to the left, move it by 4. So the trick here is you just do it carefully. 1, 2, maybe not quite like that. You do 1, 2, 3, 4. And the reason why you do it like this is because then it allows you to leave those spaces and you won't make a mistake. So you say something like this. So you get rid of that one there. The decimal's not there anymore. In fact, I'm going to go like that. And then you just sort of read out the number. So it's 0.000209. Okay, that's all you need to do. Work out the value of 1.6 times 10 to the 8 divided by 8 times 10 to the minus 4. Couple of ways you could do this. The first thing I would do is I would make this into a fraction, because this often sort of gives people ideas straight away. So if I do something like this, what could we do next? Well, lots of things we could do. I'm going to put the numbers together and the times 10 bit together and see if it gives you some ideas. So I'm going to say that that is 1.6 over 8, and then that it's also 10 to the 8 over 10 to the minus 4. 1.6 divided by 8. Oh, that's very close to 16 divided by 8, isn't it? So I'm going to cheat a little bit. So I'm going to borrow one of those powers of 10, make that a 7, and then make this into 16. Can you see why? 16 divided by 8 is much, much nicer, because it's 2, isn't it, straight away? 10 to the 7 divided by 10 to the 4. So do you remember your power rules? Do you remember what to do in a situation like this? Well, what you do when the base is the same and you divide is you take away the powers. So for example, that would be like that. So what's 7 take away minus 4? 7 take away minus 4 is actually the same as adding 4 to 7, isn't it? So it's 11. So final answer is going to be like that. 2 times 10 to the 11, and that's actually already in standard form. So you had to check that you needed to do that. A customer buys a camera, 15% sales tax is added to the price of a camera. 15% tax is added. Okay. The customer then has to pay a total of $450. The customer buys a camera, a 20% sales tax is added to the price. So the customer then has to pay £480. How much is it with no sales tax? So at the start, the normal price we could call 100%. If the price has gone up by 20%, it now represents 120%. So if 120% is £480, how do we find out the original, which is, 100%? A good way to do this is to find an in-between number. So 20% is a nice in-between number. How do you get from 120 to 20? You divide by 6. So over here, we would have to divide by 6 as well. 48 divided by 6 is, in fact, 8, isn't it? So that must be £80. how do you go from 20% to 100? You times by 5. So that suggests then that the original is £400. That's one way that you could do it without a calculator. If you did have a calculator, I would just type in 480 divided by 1.2 is the way to do that. Okay, question 10. Show that x plus 2 times x plus 3 times x plus 4 can be written like this, where these are positive numbers. So how are we going to do this? There's a video I put up here that shows you how to do this, but the idea is you pick any two brackets to start with and you multiply them, you get your answer, and then once you've got your answer, you multiply by the next one. Let me show you what I mean. So x plus 2 times x plus 3, you work that one out first. That is x squared plus 2x plus 3x plus 6. If you collect all the pieces together, what do you get? You get x squared plus 5x plus 6. So that's done. You now take your answer and you multiply it by the one that's left over, which is x plus 4. X plus 4. And you do your grid again. X times x squared, x cubed. 4 times x squared, 4x squared. X times 5x, 5x squared. 4 times 5x plus 20x. 6 times x plus 6x. 6 times 4 plus 24. Now you add all these bits together. What do you get? You get x cubed plus 9x squared plus 26x plus 24. And that's that. Really, really, really quick. 3 marks. The graph of y equals f of x is drawn on the grid. That doesn't really mean anything. It just means here's a graph. Write down the coordinates of the graph's turning point. Okay, well, that's just where the graph turns. So it goes down, 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 and then it goes back up. So we're interested in this point here. Okay, where is that? I would say that that is 1 minus 3. Estimate the roots. The roots are where it cuts the x-axis. It's these ones, okay? It says estimate because it might not be perfect, but you should try and be careful if you can. That's 2.5, that's 3. That's the middle, which is 2.75, and it's slightly less. So I'm going to say something here for that one. It could be 2. I'm going to go with 2.7, I think. Okay, and that should be fine. As long as I'm a bit careful, I should be all right. How about over here? So similar sort of idea. That's minus a half. That's minus 1. So in the middle must be minus 0.75. It's closer to the minus 0.5. So I'm going to say that's minus 0.7. Okay. So those are my estimates. Use the graph to estimate f of 0.5. So what's happened is the x bit normally has become 0.5. So they want you to make the x 0.5 and have a look at what value you get. So I would say that's really quite close to the middle of those. So I think I get minus 2.75. And that's it. Okay, we've got indices question. So find the value of 36 to the power of minus a half. So you can answer this by doing the half and then the minus, or the minus then the half. I'm going to answer the question like this. So half means that I need to do the square root. So the square root of 36 is 6. So inside that bracket, that becomes 6. 6 to the minus 1 means the reciprocal. So we're just going to just say 1 over 6. Okay, that's the way we could do that. Let's do this one. Similar sort of idea. I'm going to do one part and then the other. So I'm going to do 8 over 27 to the power of a third. And then I'm going to square the result. The power of a third means that I'm going to do the cube root. So what's the cube root, for example, of 8? what number do you multiply by itself? You know, it appears 3 times to get 8. Well, it's going to be a 2. And for 27, the number we're looking for is a 3. 3 times 3 times 3 is 27. Sorry, that's a 3. That's just the inside bit done. I still need to square it. So squaring means 2 times 2 and then 3 times 3. So my final answer is 4 over 9. Next question is question 21. Number 13. The table shows a set of values for x and y. X is 1, y is 3, x is 2, y is this, and so on and so on. Y is inversely proportional to the square of x. Okay, so how do we write that? Y is, well, it's a proportional statement. Inversely means it's going to look like this. Okay, the square of x means when you do x squared. So if we have something written like this, you are always able to take this sign and find a way of writing it like this. And I'm going to put the k and the 1 together, okay, like this. And that's what they want you to find. They want you to find an equation for y in terms of x. So how do you get this value here? That's the number that you need to work out. Well, we want to use these values here. So I'm going to pick, I'm going to try and pick the first one, and I'm going to see what happens. So when y is 3, x is 1, I'm going to put those numbers into this one here, okay? So when y is 3, it'll be 3 equals, k I don't know, k is the sort of the constant, the missing number I need to work out. X squared just means 1 squared, so 1 squared, which really is just 1, isn't it? So do you see that it's just sort of solved itself? So k is actually equal to 3. So all you need to do is you need to put that now in there, and that's the whole thing done. So y equals 3 over x squared. Done. Find the positive value, okay, that's a bit suspicious, let's look out for that, of x when y is 27. So that was A, this is B, so it could be connected, it's the same equation. So I'm going to use this equation that we just worked out. And what is x when y is 27? Okay, so 27 is equal to 3 divided by something squared. How can I fix this? Well, you can times by x squared both sides to do 27x squared equals 3. And then you could divide by 27 both sides. So you get x squared is 3 over 27. 3 over 27, you can simplify that, can't you? 3 goes into both, is in fact 1/9. And now we need to square root that. So that's why perhaps it says positive value. So square root this is the same as square root in the top, square root in the bottom. So it's going to be 1/3. So that is the answer, it's 1/3. If you want a shortcut for this one, so a little shortcut you could do is you can make this into 1 over 27. It's not over 1 over 27. 27 over 1, because that doesn't change the value, equals 3 over x squared. And then you can just turn both sides upside down. So that's another way that you could have done it to speed it up. Okay, in a puzzle there are blue shapes and red shapes. Blue shapes, and it seems like a perfect time to use the color red, and red shapes. Some of them are triangles. All of the other shapes are rectangles. Okay. The ratio of the number of blue to red is 5:3. Sorry, 5:9. The ratio of the number of blue triangles to the number of blue rectangles is 2:3. Red triangles, red. Right. Okay. We're in danger here of getting really overwhelmed with the information. So what I'm going to do before we go too much further is I'm going to try and represent this information somehow. And the way I'm going to do it is I'm going to say blue, red. I'm going to make one of these grids again. So triangles, rectangles, and I'm also going to do another column here, and this is for kind of all shapes. Okay, so there are only blue or red shapes. There are triangles, rectangles, and sometimes they talk about all shapes. They did it in this line here, the ratio of blue shapes to red shapes. So that's why I've drawn that line. What am I going to do next? I'm going to try and put these ratios on the diagram. So the ratio of the number of blue shapes to red shapes is 5 to 9. So I'm going to do that one there. Okay. The ratio of the number of blue triangles to blue rectangles, let's do that one now. So blue triangles to blue rectangles, 2 to 3. Now I'm using this table a little bit differently, okay? So it's all right if things don't add up and so on. What's important is that I keep the ratios together. So anything I do to these, I've got to do to both parts. The ratio of the number of red triangles to red rectangles is 3 to 7. So 3 to 7. Okay. Work out what fraction of all the shapes are triangles. Okay, so how are we going to do this? Well, we need to make the numbers work for us, first of all. So what do I mean by that? Well, if you have a look at the red column here, there are 3 red triangles for every 3 rectangles. But then at the bottom, we're saying we've got a ratio that's using 9 in it. So this doesn't really link up. So this is not good. So what I'm going to do is I'm going to scale up this ratio. And I might have to scale this one up as well, so that they sort of fit together. And the way to do that is to think of a number that will make them all work together. So I've got 3 parts here and 7 parts, and in total it will need to make this many parts here at the bottom. So what I'm going to do is I'm going to use a number that works with this together, which is 10, and works with this number, which is 9. So what number will work really well together for 10 and 9? It's the lowest common multiple, it's 90. So this multiple of 90, I'm going to scale things up so that these parts add to 90 and that this part adds to 90. Let's do the red bit first. So together it represents 10 parts. So if we go from 10 parts to 90 parts, we need to times by 9. So instead of writing it as 3 to 7, I'm going to multiply that up by 9. So 3 times 9 is 27. 7 times 9 is 63. So am I allowed to just do that? Well, yes, I'm definitely allowed to do that because this ratio here is the same as this ratio here. And it's actually still correct the way that I've written it, but as we said, I'm going to kind of get things to line up. So how do I make my 9 about 90? Well, I times it by 10. So if I multiply that part of the ratio by 10, I need to multiply that part of the ratio by 10. So that would now be 50. Okay, does everything line up on the rest of it? So blue parts, 2 to 3 parts, representing 50 parts total. No, that doesn't work. So we're going to do the same trick again now. 2 and 3 together is 5, which already fits into 50. So I'm going to change this ratio so that it now says 20 to 30. So why have I done all of this? Well, I've done all of this because now all of the ratios work with each other. So you can sort of read them across. You can sort of read them any way that you like. So you're ready to answer this question. It doesn't mean that there are 50 and 90 here, but there could be, okay? It's possible. This could be true. So work out the fraction of all the shapes. So all the shapes in my situation is out of 140. There are triangles. Well, how many triangles? Well, there's sort of 20 parts here for the blue and 27 for the red. So it's 47 out of 140. So if you get this kind of question, it's quite a tricky question, but this is one way you can answer it. It's about drawing the table and combining the ratios. Try and make it a bit more visual so you're not sort of balancing so much stuff in your head is my advice for this one. Number 15. A cone has a volume of 355 centimeters cubed. The radius is 2.1. They've told us the volume of a cone. work out an estimate of the height of the cone. So what is the height? Now we don't have a calculator and it says estimate. So we need to do some rounding on this one. That's what we need to go for. How am I going to round these numbers then? So I'm going to have a third. I'm going to be using pi. Pi is 3.14. So what's that really close to? It's really close to 3. So I'm going to be using 3 for this number here. R, so 2.1. So 2.1 is very, very close to the number 2. So I'm probably going to use the number 2 instead. The height is what I'm trying to work out. Okay, so the volume of a cone, what number should we round that to? Well, it's not immediately obvious here, okay? What's it quite close to? We could say 400. Or we could say to the nearest 10 is 360, isn't it? Let's write everything down and see if an idea comes to us. So the volume of a cone, so the volume is going to be equal to, let's do the other parts first. A third, so just try putting some numbers in is a good way to start this, times 3, so I'm using pi as 3 because it's an estimate, times 2 squared times height. Well, a third times 3 cancel each other out. 2 squared is 4, so 4h. Okay, so what could the volume be to help make this work? Well, it doesn't really matter. In fact, there's multiple answers that may be accepted. So I would say here that you probably would have gone with 400. So how does that work? Does it work out for us? Well, yes, if we divide by 4 on both sides, it's telling us then that the height is 100. Okay, so the height is 100 centimeters. It's not the real answer, but it's an estimate is the idea. So Mary uses a calculator to find the height of the cone to 2 decimal places. Will our estimate in part A, so will this number here be higher or lower than Mary's answer? So Mary has the real answer. So is Mary's answer going to be higher or lower? Well, what did we do? We had our 400, and in effect we divided, okay? So we've in effect sort of divided by a third. So this bit's a little bit tricky, okay? But a third times 3 times 2 squared. That's another way of thinking about what we did. So we rounded these numbers. So how did we round them? Well, the 400 went up. The 3 was a result of going down, and the 2 was a result of going down. So if you put all your numbers that you start off with in your numerator up, and you divide by less, what's going to happen to your answer? Well, you're going to get a bigger answer. So this 100 is actually bigger than the real answer. It's bigger than Mary's answer. So it's bigger than Mary's answer. So higher. So it's higher because the numerator was rounded up and the denominator was all rounded down. Okay, and that would be enough. All right, let's have a look at this one then. So, n is an integer greater than 1. Prove algebraically that this is always an even number. Okay, how to get started? So a couple of things to remind you. An even number in the world of algebra is something that is written in the form of 2 blah, okay? Stuff or blah or something like that. So if you can make something fit that format, well, you know, when you've got n's and stuff in here, you can pull a 2 out, that means you've got an even number. We need to prove algebraically. So if we're proving algebraically, we do not want to be putting numbers in like, you know, you can't just shove a 3 in here. 3 squared plus 4 plus 3. If you do anything like that, that's wrong all day. That's not algebraic proof. So start with what they've got here and try and play around with it and see if you can get it in this format. So n squared plus 4. Okay. How about this n plus 2 squared? I can see that that might cause some issues. So n plus 2, n plus 2. Let's quickly work that out. Okay. So n squared plus 4n plus 4. So what's going to happen is I'm going to get n squared plus 4 plus n squared plus 4n plus 4. And if I collect this all together, what will I get? I'll get 2n squared plus 4n plus 8. So can I make that fit this format? Well, yes, because I can take a 2 out of everything. So if I take a 2 out of everything, what would I get? I'd get n squared, because 2 times n squared is 2n squared, plus 2n plus 4. Okay, and that's it. That's all we need to do, because 2 times something is going to be an even number. When I say something, by the way, these are integers, okay? So we're not dealing with decimals or anything like that, okay? So 2 times some stuff about integers is definitely going to be even. That's it. There are 12 counters in the bag. 8 of them are red. Now we've got red and blue again. 8 of them are red. 4 of them are blue. Nina takes at random 2 counters from the bag. So she's going to take the thing once. She's going to take the thing twice. Does it sound like she's putting anything back? I would say no. So I would call this a no replacement situation. It means that the probabilities, because this is a probability question, will change. Work out the probability that Nina takes 1 counter of each colour. Okay, this is calling out for us to do a tree diagram, this question. So, picking the first time, picking the second time. Let's go red, red, and then let's go, whoops, I'm missing another red. And then let's go blue, and blue, and blue. So what does this mean? Well, this is a way of thinking about what happens. So you could pick a red first, and then pick a blue, for example. You could pick a blue, and then a blue. And what we're going to do is we're going to put some numbers on these branches, and you're going to use these numbers to find out stuff you want to know. So if there's 12 to start with, and it's at random, it means these things here are out of 12. Red, well, there's 8. And blue, there's 4. And, you know, we're assuming here they're equally likely to be picked. Okay, so what happens, let's put yourself in the situation. What happens if you've picked a red one? So how many red ones would be left now? Well, 7 would be left. And how many counters would be left in total? Well, there would be 1 less. Let's do the same again. Let's imagine you picked a red one. So how many blue ones are left? Well, all of them. All 4 of them are left. And the same idea, we've removed 1, so it's out of 11. Do you notice how these numbers add up to 1? So that's a powerful shortcut to be using. Let's do this one over here. So you picked a blue one, and now you pick your, well, hey, let's go back. You picked a blue one. So how many counters are now left in the bag? Well, there is 11. You could do that on both of the branches if you like. If you picked a blue one, how many red ones are left? Well, all of them are left. All 8 of them are left. If you picked a blue one, how many blue ones are still left? Well, 1 less. So 1 less here is 3. Okay. Now, if you want to work something out, so say you want to work out a red and then another red, all you do is you multiply those together. That's it. We want to work out one of each. So what does that actually look like? Well, that looks like a red and then a blue, or it looks like, what's the other alternative? A blue and then a red. So it could also be a blue and then a red. Or kind of means and in lots of situations, a probability like this. So we're going to work these out, and then we're going to add them together. That's all we're going to do. So red and then blue is going to be 8 over 12 times 4 over 11. Blue and then red is 4 over 12 times 8 over 11. 4 over 12 times 8 over 11. Multiply the tops together, multiply the denominators, you get 32 over, what we've got here, we've got 12 times 11, so it's going to be 132. And then the other one, it kind of works out to be the same multiplication, doesn't it? So in total, it's going to be 64 out of 132, and that's all we have to do for this. It doesn't say you have to simplify, so it should be fine. Okay, question 18. The rhombus ABCD is drawn above. Rhombus is quite a special shape, isn't it? So on a rhombus, they'll all be the same length, okay, which might be useful. The coordinates of A are 3, 7, so that's 3, 7. The equation of BD, if you say something like BD, what that means is it means that you're drawing a straight line from one to the other. So the equation of BD is, that's a mistake there, is 2x plus 1. Okay, so this is y equals 2x plus 1. Find an equation for the other diagonal AC. So how about this one here? What's this one going to be? Well, there's a couple of facts we need to know. So the first one is the equation for a line. There's two ways of doing it. Probably the most common way of it is writing it like that. Y equals mx plus c. What does it need? Well, to find this out, you need two bits of information. In fact, I'm actually going to write it the other way around because I think this is more useful for this one. This is another way of writing the equation of a straight line. You need a coordinate. So if you want to find the equation of a line, you need a coordinate and you need the gradient in general. So the good news is we've already got a coordinate, 3, 7. So how about the gradient then? So this is when you need to know something about a rhombus. So in a rhombus, the diagonals are, any guesses? Can you see it approximately? Well, they're actually perpendicular. Okay, the diagonals are perpendicular, and we need to know that. So for perpendicular lines, the rule is that they are the negative reciprocal of each other. So for example, if the gradient for one of the lines is 3, if it's perpendicular, for the other one, it will be minus 1 over 3. Let's do another one. If this is, say, 2 over 7, then for the other one, it will be minus 7 over 2. So what's the negative reciprocal of 2? Well, it's going to be minus a half. So I've now got the gradient. So using minus a half and using 3 over 7, I'm going to write it in this format here. So y minus 7 equals minus a half of x minus 3 is the equation of this line. And I'm going to do a little bit more work on this now. So y minus 7 equals minus a half x minus 3 over 2. And now I'm going to add the 7 to the other side. So y equals minus a half x. This is like minus, well, probably the easiest way to do this is just put that as 14 over 2. 14 take away 3 is 11 over 2. Okay, and that's the way I would leave my answer for this. Minus a. OC is just plus c. And then CD is this new bit that I don't know, which could be quite useful probably. Okay, let's try and simplify this a little bit. So half a minus a is just minus a half a. Minus a half c plus c is just plus a half c. I've got 4c here. I've got minus a half a there. Okay. if I move the rest of this stuff to the other side, I should be able to find out what CD is on its own. So let's take away the half C from both sides. 4 is the same as 8 over 2, so that would be 7 over 2C. And then if I just add a half A, that will take care of that one over there, actually. So what this has done is it's told me what CD is. CD is 7 over 2, or that's 3.5 C's. Let's go back to the question now. So OC, this bit here, to this bit here is in the ratio of something to 1. So what's that ratio? Well, 1C would be 1 to 3.5, but that's not quite what it wants. In this case, it wants the 1 on the right, so I need to divide both sides by 3.5. So 1 over 3.5 to 1 is the ratio. In other words, it's trying to tell me that the bit on the left is a lot shorter than the bit on the right. So final answer you can leave as 1 over 3.5. Solve algebraically these simultaneous equations. In this kind of situation here, we want to go down the substitution route because we've got squareds and non-squareds. So you want to substitute. Y is just y, this is 3x. So I'm going to get the second equation and I'm going to put the y on its own. So y minus 3x equals 0. I'm going to change that to y equals 3x. For the other equation, which was x squared plus y squared equals 40, I'm going to write that out, but the y I'm going to get rid of. So I'm going to write it out now as x squared. Remember, I'm going to get rid of this bit, so I'm going to give myself some space to work with. So something squared equals 40. And now the y from this bit is going to become just that part there. Okay? So x squared plus 9x squared, that's right, it's 9x squared equals 40. 10x squared equals 40. Which means x squared is 4. If x squared is 4, x actually has two answers. I can think of two answers that can be multiplied by themselves to give 4. The number 2, but also the number minus 2. Okay, and we're not finished. So let's look at 2 and minus 2 separately. So if these are the x values, what are the y values? Because we're looking for x's and y's. Well, you're going to take your value and put it into an equation that's useful. I would suggest this equation here is very useful. How do you get your y? You do 3 times your x value. So 3 times minus 2 is minus 6. And same over here, you do 3 times your x value. 3 times 2 is 6. Okay, so that's what we're looking for. So minus 2 minus 6 or 2, 6. And make it obvious that these go together and these go together. The quadrilateral ABCD is shown below and it's got some information on it. So they're trying to show me that these are the same length by the look of it, and probably that these are the same angle. That's usually what that means. AB equals CD. Okay, yep, I knew that. BAD equals ADC. So these are the same as each other. Prove that the diagonals of AC and BD are equal. So how could I prove that that line there is the same as that line there? Well, the quadrilateral ABCD is drawn below. AC is equal to BD. Angle ACB is equal to angle BDC. So it's a slight typo there. That should actually say angle ACD. Okay, so ACD is going to be equal to BDC. And that's how I could draw it to represent it. So prove that the diagonals of AD looking like this, and BC looking like this, prove that they are equal to each other. So how am I going to do that? Well, I might be tempted, first of all, to just kind of draw them out separately, because this diagram could get really, really confusing. So what was it? AD and BC. So AD and BC. I'm going to draw one then that looks a bit like this. So that's going to have A and C and D in it. And then I'm going to draw sort of the other one, which is a bit like this. And that has C and D and B. So how could I prove that these ones are equal to each other? Well, now I've got triangles, maybe an idea comes to mind. I could prove that they are congruent triangles. In other words, they are the same triangle. Because if I can prove that they're congruent triangles, then these must be the same. So if I put on the information I know first of all, those sides are the same, and this angle is the same. So is there anything else that I know about them? Well, this one is the same, isn't it? Because it's common. It's common. It appears in both. So we've got a side, we've got the included angle and another side being the same on both shapes. So ACD and I'm going to call this BCD are congruent through side angle side. And then I'm going to say that AC is equal to BD. The included angle, probably don't need to say the included angle, but that's what it means when you say side angle side. It means the one that's between them. It's called the included angle. So it has to be that particular angle rather than other ones. So the included angle is equal, and then CD is common. Finally, sort of the link is, so that's most of the hard work. As they are congruent, the remaining side must be the same for both. Okay. And then that's just saying that when you have these three bits of information, you're going to get a particular result. And again, if you do a calculation with these 3 bits of information to work this side out, you're going to get the same result as well. In fact, you'll know this from the cosine rule. This is the cosine rule. If you use these, cosine rule gives you that. So you'd be putting the same information in, so you get the same answer. And that's it.